Great. Okay, so today's lecture, so this had also a pre-lecture video that was about 15 minutes long about using what are chemical formulas and how to use them as conversion factors. So I trust that we saw that video. If you haven't seen that video, then this lecture, there will be some parts that might be a little new, to put it mildly. So please be aware of that. The pre-lecture goes in the same place as all the videos for lectures, so synchronous lecture page. And then we had a pogle to sort of introduce what's going on in this lecture. So what our goal today is, so we're still sort of looking at matter from both the large perspective and the small perspective. We've talked about the phases, which is sort of the group behavior of what particles do. And now we want to not just identify a label for the composition. This is a gas, this is a gaseous mixture, but also be able to quantify composition, be able to say it's not just a gas made out of nitrogen molecules and oxygen molecules, but actually have a number that we can calculate that goes with it. And the first step is to be able to count particles effectively. As you recall, particles are that we're referring to in chemistry are extremely small, so small that we can never see them with the naked eye. We can only sort of visualize them with very powerful instruments that that sort of visualize through microscopy and so forth. So how exactly do we have conversations about counting particles, atoms, and molecules? Well, that's kind of what the pogle introduced with the idea of molar masses. So that's going to be the focus of today's lecture. And then we're going to use molar masses, not just in the next lecture, which will be a major focus, but molar mass is the #1 sort of conversion that's used from this point to the rest of the course, to the conclusion of the course. So it's one of the most important types of conversions that we can do. So we focus on that today. But before we do that, I have something that that we can use to sort of guide ourselves or orient ourselves. Why are we learning a new conversion factor? Well, I use sort of the backdrop, the setting of a carnival to sort of introduce how it can be used on an everyday scale. So I don't know if you've ever had this experience or played this game before. Usually it's like at a carnival or a party where you are asked by the host, how many jelly beans are in this jar? So if you can count them, whoever is closest to the right number gets a prize or something along those lines. So I don't know, is it just me or do we know this game? I hope we do. It's, you know, I'm gonna show you how to cheat on this game. So if ever you have the ability to play this game, we can sort of utilize a few tricks. So basically, the idea is that we want to know how many jelly beans are inside this this jar, but we can't open it, and it's going to be impossible to count the interior beans by jelly beans ourselves. So what can we do to sort of sneaky get our answer? Well, one idea is that maybe I could use conversions to figure out what the answer will be. So one way we can do this is actually, instead of counting, we could weigh the container of jelly beans. And in this case, we'd have to be mindful to subtract the weight of the container because that's adding extra weight that we don't need. So say that we have jelly beans inside this container and the total amount is equal to 1.03 kilograms. Now, how does this help us? Well, if there's a way that I can relate how heavy a jelly bean is to how many jelly beans there are, then by our knowledge of conversion factors, if I have a number that connects how heavy to how much, then I'd be in business to figure out how many jelly beans are in this jar. And so that's exactly what we might want to do. Though if we're at a house party or a carnival, we might not have access to a chemist grade scale or balance used to weigh things. So if I try to weigh an individual jelly bean, it would be probably too light to register on, say, a kitchen scale. Maybe the scale only weighs kilograms. So I need some way to circumvent or to go around this problem. So one idea is, if one jelly bean is too light, maybe I should weigh a group of jelly beans and just be mindful of how many are related to this number. So perhaps we decide to group our jelly beans into a group, and let's give it a name. A group of jelly beans is called, I don't know, I made this up, a jumble. So 5 jelly beans is one jumble. And then I can say, well, if I put a jumble of jelly beans onto a kitchen scale, they come out to 0.558 kilograms. So now I'm starting to get in business because I want to be able to count how many jelly beans I have. And I have a relationship. Well, this many jelly beans, one jumble of jelly beans is going to be 0.558 kilograms. Oh yeah, did I say 500? So one jelly bean is too light. So a big group of jelly beans, and I just say a group of jelly beans is a jumble. So thank you. So we have this information. So now the question is, I have the numbers that I need. Now let's go ahead and put them together in order to figure out approximately, because maybe this isn't too accurate with the kind of numbers that I'm using, how many jelly beans are going to be in this jar. So the jelly beans in this case weigh 1.03 kilograms. I have 500 jelly beans in a jumble, and one jumble is 0.558 kilograms. So we can go ahead and rewrite our information. 500, and I'll say to the nearest one, so 500 with 3 significant digits, jelly beans is one jumble. So remember, anytime I have a relationship where this much is equal to that much, that can be a conversion factor. So now I'm just setting up my conversion factors and seeing how they're going to relate. So that means this is 0.558 kilograms is one jumble of jelly beans. So this becomes our conversion problem. I want to convert the weight of my jelly beans into the total number of jelly beans. So essentially, this is my given unit that I want to convert. And now I have fractions, right, that can be used as conversion factors. So let's go ahead and set this up and find out how many jelly beans we have. So again, we think of the 1.03 kilograms of jelly, and I'll just abbreviate it as jelly, as the number we want to convert. And now I use my conversion factors to get to my desired outcome or my desired unit. So which would be the number of individual jelly beans. So again, we start utilizing similarities in our units. I see kilogram, kilogram as connection. They're both units of mass. So that's going to be 0.558 kilograms of jelly beans this is my made up unit, a jumble of jelly beans. When we do that, my unit of mass cancels and I have a jumble. Now, what am I going to do? I'm going to use my second number. One jumble of jelly beans is 500 jelly beans. That cancels out my grouping. I canceled those groups. So we plug this into our calculator. I now have the units I desire. This will count individual jelly. I end up getting 922 jelly beans. So this would be what I would maybe suggest as the answer, and perhaps I get it right. Maybe there are probably a few other variables that might limit how accurate I am in this scenario. Maybe you can think of a few. But what we're doing here is we're demonstrating an important property, an important sort of fact that we'll utilize in the rest of this lecture. It's the idea that by connecting some measurement that I have limited ability to observe, by connecting it to something that I have a better ability to measure, we get our answer. So in this scenario, I don't really have the ability to count jelly beans individually. It's too hard. So I connect it to something that I can measure easily. How much do jelly beans weigh? And then we have this strategy that, again, is going to be utilized over and over in this class, where we go from a weight to a group of objects to individual. And maybe I'll say individual number of particles. And so this is the analogy. In fact, this is very similar to the calculations we're going to be doing today. This is very similar to what we're going to be talking about. So to connect the dots a little bit better, in our case, in chemistry, instead of jelly beans, we want to count the particles inside a box, for example. So instead of this carnival game, the question will be, well, how many particles are there? Well, in this case, we made up what a group of jelly beans is called, but that's really going to be our mole conversion. So we recognize that whenever we're creating a group of something, we're creating that conversion factor. That's identical to when we created, or we introduced, I should say, Avogadro's number as a conversion factor. The only thing that's a little bit different is that we haven't introduced this conversion factor, which is saying that a group of particles is equal to some weight, or some mass, I should say. That's what the focus is today. Molar mass is that conversion factor. It is the quantity of grams that a mole of particles will weigh. And so by performing this calculation with jelly beans, we sort of connect the analogy that our weight to group of particles will be one of these conversion factors, and our group to individual particles, well, we already know which one that is. That's going to be Avogadro's number, connects a mole is this many particles. And so we can see that in our calculations, we might be using Avogadro's number, which is symbolically N sub A. So that's kind of our idea here. And let me know if I'm going too fast, please. So molar mass, that's the focus, and that's what you saw in your POGL. It's the mass of 1 mole of substance in units of grams per mole. So one thing that I'd like to emphasize, and we've seen this many times, is that whenever a unit has a slash mark, we should think of it as a fraction that we could write in our math. So this should be a giveaway that with a unit like this, molar mass is a conversion factor. So that's going to be our important conversion factor. So there's some good news. We can reuse what we learned yesterday. The molar mass of all atomic elements is equal to its atomic mass with units of grams per mole. So what this means is that you don't need to do any extra work to go into, to find a molar mass. If I want the molar mass of carbon, it's literally the same number as what we learned previously as the average atomic mass. They do double duty. They do 2 for 1. So this is both the atomic mass and what we call the molar mass. So we would say as an atomic mass, 12.01 represents the average carbon atom in AMU. But it also means that 1 mole of carbon is equal to 12.01 grams. That's the definition of a molar mass. It is the mass of 1 mole of a substance. So this means that your molar mass, which I give capital M for carbon, is 12.01 grams of carbon per mole of carbon. It's a simple extension to do more complex molecules, so particles with more than 1 atom. For compounds, because of conservation of mass, the molar mass of a molecule / compound is equal to the sum of the molar masses of its constituent atoms. So for example, if I wanted, what is the molar mass of table salt, NaCl? Well, this chemical formula tells me I have 1 sodium and 1 chlorine. So I am going to look at my periodic table. Oh, hopefully we have our periodic tables from before because we are going to be using them. So we look and we say, well, the mass, the number below sodium is 22.99. So that's the average weight of a sodium atom in AMU, but it is also how much a sodium atom, or sorry, a mole of sodium weighs in grams. So 22.99 would be the value that I use for sodium. 35.45 is the bottom number for chlorine. And I get 58.44, and the unit again, grams per mole. So what this means is that if I wanted a mole of NaCl particles, I would need to scoop out 58.44 grams to ensure that value. That's what a molar mass does for us. It connects counting to something that we can do easily in a lab or even our kitchen, right? If I weigh something and I have a conversion factor, it connects to counting things. We explore in the POGO a little bit, why do these numbers come out to such sort of happy values that we can see from the periodic table? So why are molar masses the same number as the average atomic mass? So you can thank Avogadro because Avogadro's number comes to help us. So we do this in the POGO, so I'll do it very quickly. So we would first ask, how much does a carbon-12 atom weigh as an example? So the conversion factor for AMU to grams is shown here. And we know that according to what we learned yesterday, that 1 carbon-12 atom, remember the 12, what do we call that? That's the mass number. It tells us how many particles are in the nucleus of a carbon atom. So there are 12. And because in AMU units, a proton and a neutron each weigh 1 AMU, then that means the weight of a carbon-12 is 12. So it's really nice. But with these conversions, we can set it up to figure out the mass of a carbon-12 atom in grams. So all I've done is I've taken, well, there are 12 AMUs per carbon-12 atom. And I use the conversion factor to say, well, how many grams is that? So I get this much. A carbon-12 atom is this many grams. Now what we do is we say, well, what if I wanted to reach the same value, but as the atomic mass, but in grams. So how many particles would it take to have a mass that's equal to the atomic mass? So for carbon, that is 12. So now my question is, how many particles do I need to get to 12 grams? Well, we ask that, well, we set it up like an equation. One carbon atom weighs this many grams. And all I've done was taken its mass in AMU, and I've given you the conversion. It's not something to memorize, it's just something to use. I know the mass of one atom. I use the conversion to figure out how many grams one atom is. Now I ask myself, how many particles does it take to reach a weight that matches in grams? So for carbon, how many particles do I need to get to 12 grams? That would be equivalent to solving for this Na value. When I do that, I get, it will take 6.0 times 10 to the 23 atoms as a collective group to weigh 12 grams. Why did I pick 12? Because 12 is a really nice number because it's already underneath carbon on the periodic table. So what I do is I do this for all of my elements. I see how much do they weigh in AMU. Then I convert that to grams. And now I ask how many particles of that element do I need to reach the same number. In this case, it was 12. And I get 6.0 times 10 to the 23, which should be sort of a nice number for us because we recognize that that is what we've been calling a mole. It doesn't have as many significant figures, but that's okay. With better measurements, we would have gotten the same number. But what this tells us is that a mole of particles is the amount that you need to reach the same number as the periodic table in grams. You might guess this will work for every element. How many helium-4 atoms will have a mass of 4 grams? By doing the same logic, well, first, how much does a single helium weigh in grams? And then how many helium atoms will I need to reach 4 grams? The number comes out to 6.022 times 10 to the 23 again. And in fact, if you do this same scenario, but replace the element and replace its atomic mass, you will always get 6.022 times 10 to the 23. That's what makes Avogadro's number a really nice conversion. And that's why we use that number rather than a nicer number. So probably some of you have thought, why do we call a mole this strange number? Why is it called 6.022 times 10 to the 23? Why not just call it a billion or a million, you know, a group of particles is a billion particles, something. This is the reason why. Because this many particles will always weigh the same amount as the atomic mass. So a mole of carbon will weigh 12 grams, right? A mole of helium will weigh 4 grams. A mole of sulfur will weigh 32 grams, and so forth. So that's why the mole is a sort of, is that odd number that we have to memorize, because in the end, it makes our lives easier. So I just want to reiterate that it's not, it's more important to understand how these calculations work than to actually do this every single time. This is just for demonstration purposes, rather than this is how we're going to solve all of our problems about this topic. It's basically my way of explaining what is a molar mass and why is the molar mass such a nice value. It's always the value at the bottom of the element, at the bottom of the element symbol. So that's what we need to take away from this. The reason why Avogadro's number is such a specific number is because it makes the conversion from grams to AMU perfect. All we do is replace the AMU with grams per mole. So what does this mean? It means that our lives get really nice, really easy. If I look at my periodic table and I take, for example, sodium, I see 22.99. So what this means is that, well, we learned yesterday that 22.99 is the average weight of a sodium atom in AMU. But what it also means is that this is the molar mass of sodium. So if I weigh out 22.99 grams of sodium and I see that displayed on my balance, then that means I should have 1 mole of sodium atoms. And remembering how Avogadro's number converts them, that means I know I have 6.022 times 10 to the 23 atoms. So that's why this is a really nice conversion. And you can do that with any of them. So gold, right? I look at the bottom number, gold is 196.97. As the molar mass, it means that if I put gold on a balance, on a scale, and I get enough of it onto the plate so that the display says 196.97, then I know I have a mole of gold there. And because of the conversion we learned, 1 mole means that I know I have 6.022 times 10 to the 23 gold atoms. And so forth. So sulfur, right? Sulfur is 32. If I weigh 32.06 grams, I have a mole of sulfur. And that's going to be this many particles again. So that's the beauty of a molar mass, because it takes all of the hard parts out of counting. I don't want to count individual atoms. So instead, I'm going to weigh them. And using this relationship, a mole of gold, a mole of sulfur, a mole of sodium weighs this much. Then I can convert a mass to counting how many. And we're going to be utilizing this over and over and over again. And so for one more sort of practice, what is the molar mass of this formula? So remember what the chemical formula indicates when I say N2O5. So what is the molar mass of N2O5? So it's a particle with 2 nitrogen atoms and 5 oxygen atoms. So our molar mass for this substance, well, we learned in the previous few slides, the molar mass of a compound is the sum of the molar masses of its atoms. So we look for, okay, nitrogen is up near the top. So I look for, well, here's the number, 14.01. So this means 14.01 grams per mole times 2, because there are 2 nitrogen atoms. Oxygen is 16.00. So plus 16.00 grams per mole times 5. What we end up getting is 108.02 grams per mole. Notice that because calculating a molar mass is addition, and these 2 and 5s, they are infinite sig figs. Because this is addition, we're going to go by decimal places. So notice that I go to 2 decimal places. What this means is that if I have a container of this substance, N2O5, if I were to scoop out exactly 108.02 grams of it, I know that I have a mole of those particles. So again, it's connecting the amount of a substance in particles to its mass. And that's a really great thing to be able to do since atoms are so tiny, we can't count them individually. Now, I said a lot of stuff in the last couple minutes. So if I'm going to pause here, if anyone needs to ask a question via the chat or in verbally, I guess, just in case. It might be one of those topics that sort of sounds easy on paper, but is a little bit harder in practice. So we are going to do quite a few bits of practice. Okay. Okay, more discussion about molar mass. So molar mass is a property of matter. It would be considered a physical property because we don't need to damage the substance to measure it. So molar mass is given the capital M. It is the mass of a mole of substance. So obviously we just went over its units are grams per mole. But one thing that I want to emphasize is that a molar mass is a ratio. Remember, ratio is the division of two numbers. So it's grams divided by moles. Now we've learned about a certain specific ratio before. If you can, you should be able to, because this is intersession. It's only been a few days since we've talked about it. But this should ring a bell when we're discussing it's just like density, but with a different denominator. So that means it's an intensive property in that the molar mass of a substance does not depend on the sample itself. A cup of water and a swimming pool of water, it doesn't matter that their sizes are different. The molar mass of water is just a single constant number. That's what the intensive property means. And the same thing goes with density, remember. If I'm measuring a cup of water versus a swimming pool of water, it's going to always be the same ratio, the same number. And so we can sort of just, for a moment, extend this to molar mass. It would be, we take the grams and we divide by the moles. In much the same way we would take the grams and divide by the milliliters to get a density, we do the same thing with a molar mass. And so hopefully it's comfortable to extend that to say, well, a molar mass should be an intensive property, doesn't change, because if I double the amount of grams that I scoop onto, say, into a beaker, if I double the amount of grams, I should be doubling the amount of particles there. In fact, that is the connection. And so the division, the ratio of the two will always get to be the same. And just to make it explicitly clear, it's that if I double the grams, I would be doubling the moles. Notice that if we're dividing the two, they'll cancel. So as long as we take the correct amount of grams with the correct amount of moles, the ratio of the two will always come out to be the same. So a molar mass is always a constant number for every substance. And that's because it is a ratio. So we can use this and exploit this definition of molar mass to sort of solve some problems to be able to find this value. So I have an example here. 1.00 gram of beefy meaty peptide, BMP, contains 1.18 times 10 to the minus 3 moles of BMP. What is the molar mass of BMP in grams per mole? And remember that the -1 is the same thing as the slash mark. So this is the same as saying gram/mole. Now, just a short aside, this is a real thing. In case you were wondering if I made this up, beefy meaty peptide. So this is a peptide. So a peptide is a molecule that's a little bit smaller than a protein. It's like a mini protein. And specifically, you probably deduce from the name that beefy meaty peptide comes from beef products. And in fact, it's believed that most of the beef flavor that comes from beef is due to a single molecule that we call BMP, beefy meaty peptide. So a little fun fact, this is responsible for beefy flavor. But I digress. Our task at hand is to find what is the molar mass of BMP. So what am I going to do? I am given 1.00 gram of BMP, and I'm given 1.18 times 10 to the minus 3 moles of BMP, and I desire grams per mole. So this is one more example of let the units guide you with what to do. In the same way that if I were given a mass and a volume, the density is dividing the two. If I'm given the mass and how many moles are there, the molar mass by its units is dividing the two. So our answer is the molar mass is equal to the mass divided by the moles. Remember that in the gas chapter, we gave mole the letter N. It's going to be 1.00 grams of BMP divided by 1.18 times 10 to the minus 3 moles BMP. When we plug that into our calculator and round to 3 significant figures, we get 847 grams per mole of BMP. So what this means is that if I'd like to count out a mole of BMP particles, I would need to weigh 847 grams on a scale. When I get to that number, it means that I have a mole of those particles on my plate. Yum. Not too bad, right? What is the molar mass of a protein in grams per mole if a single protein has a mass of 1.115 times 10 to the minus 20 grams? So this is a little bit different because it's a single particle, and we know its mass in grams. Again, we can use units and dimensional analysis to guide us. We are given versus we desire. I have one protein equals 1.115 times 10 to the minus 20 grams. I desire the molar mass in grams per mole. Again, I use the units to guide me. One protein is that many grams, but I'd like to know how much a mole of protein will weigh. So I want to go from an individual count to a group called a mole. So what number am I going to use to go from individuals to a group? It's Avogadro's number, right? Avogadro's number is the how many to a mole, and it's 6.022. So how am I going to set it up? Well, I have 1.115 times 10 to the minus 20 grams. What do I desire? Grams are on top, which they already are, and I want mole to be on the bottom. So that's going to be mole needs to be on the bottom, and that implies 6.022 times 10 to the 23 is on the top. So it's 1 for that. What does this come out to? 6715 grams on top, moles on the bottom. In other words, all I've done is I've taken the mass of one particle and I've multiplied it by a mole of particles. So if you want to think of it in terms of like a formula, one particle's mass multiplied by a mole of particles is a mole of particles mass. This is about 6.7 kilograms will be a mole of protein particles. What this suggests is that proteins are pretty huge. They're pretty large. Because in order to count a mole of protein, I actually have to weigh a lot of it. This implies that protein molecules are pretty big. Though that's not necessarily something that's not necessarily intuitive when you first think about it. So I'd like to discuss that a little bit more to make sure we understand how to interpret the size of a molar mass. And again, at any point I need to clarify something, please let me know. So one thing that's sort of jarring is the fact that we're counting the same number of particles, but why isn't the molar mass a single number? Why is it that every single substance gets its own molar mass? So I just wanted to visually depict the difference between an element with large particles versus, say, an element with small particles. So larger mass particles versus smaller mass particles. So visually, if we were to just sort of connect this to a cartoon, say that a gram is represented by a box like you see here, then we could ask, well, how many particles of element A fit into a gram? And how many particles of element X also fit into a gram? So if I try to fit these particles into a box, what I would find is that a bigger particle means that less of them can fit into a gram. But if I have a smaller particle, relatively speaking, more of them fit into a gram. So the reason why molar masses are different is because the size of these particles affects how much you have to weigh, which hopefully is a bit intuitive. But I like to think of it as kind of like a pound of feathers versus a pound of bricks analogy. So I don't know if you've heard this riddle, or maybe I don't know if it's considered a riddle or a joke. Let me know if you have. But the idea, someone asks you, which weighs more, a pound of feather or a pound of bricks? And then what do you say to that? I'll give you $5 if someone's trying to be a smarty pants and is like, which weighs more, a pound of feather or a pound of bricks?
They weigh the same.
Yeah, and that's why they're trying to be a smarty pants, because they're trying to catch you in a trick. They weigh the same because they're both a pound, right? So why is it? But I guarantee that some of us, including myself, probably when we first heard this, would have said, oh, the feathers, right? The feathers are what would weigh less. So why do we jump to that idea? It's kind of the same reason that we have this scenario to our left. It's because feathers are lighter than bricks. It means that we need more of them in order to equal a certain weight. In the same way that I need to add more particles here to fit into a gram, and less particles are needed to fit into a gram here. So this means that things that are lighter particles will have smaller molar masses, And things with larger particles will have higher molar masses. And that's because if we're trying to fill to a certain amount of grams, we don't need as many of the larger particles. So this is why each element has its own specific molar mass, because their particles are different, in this case, masses, though it's analogous to sizes. They're different masses, and so we would need a different amount in order to count a mole of particles. And so with this, if this is making sense, we could answer this question: which contains more atoms, 3 grams of carbon or 3 grams of copper? So just in case, it's sort of written right here. These are the molar masses, though you could look them up. So the molar mass of carbon is 12.01 grams per mole. The molar mass of copper is 63.5 grams per mole. So if I'm trying to fit as many particles into 3 grams, which one will have more particles? It's going to be carbon. Carbon has a lighter molar mass, meaning it doesn't take as much to fill out 1 mole of substance. This implies correctly that we will get more particles per gram from carbon. Again, the idea is that carbon has a smaller amount of mass to reach a mole, whereas copper needs a larger mass to reach a mole. So when I reach 12 grams with carbon, I will reach a mole of carbon atoms. But if I weigh 12 grams of copper, I have not reached a mole of copper atoms. I need to get to 63. So this means that if we're weighing the same amount of 2 elements, the one with the smaller molar mass, which is a little bit, it's an inverse relationship, you could say, the one with the smaller molar mass will have the most particles. And it's a little bit trippy and a little bit confusing, but it has to do with the fact that there's a size difference in terms of mass. But so I ask you to sort of ponder that, make sure it makes sense as you think about this topic. So, but that's the important thing, to connect the idea that this number represents how many particles, well, how many grams are in a group of particles. 12.01 means 12.01 grams are necessary to weigh a mole of particles. Okay. If you want, you could actually prove which one has more particles by converting this number. We'll do that in the next couple slides. Okay. Molar mass. We use molar masses to convert chemical amounts to masses, hence the name. So again, we use the fraction in its fraction form. And if it helps, go back to that analogy of the eggs versus and the dozen. Each dozen eggs weighs, and I just made this number up, 24 ounces. So we would say the dozen weight is 24 ounces per dozen, right? Each group of eggs weighs this much. So this is analogous to a molar mass. It's doing the same thing. A certain quantity of eggs weighs a certain amount. A dozen eggs weighs 24 ounces. So our conversion factor is 24 ounces per dozen. The same thing goes with the molar mass. It's a certain amount of grams per mole. And the weight that it actually comes to depends on the size of the particle. And I'm using size kind of sloppily. What I mean is by mass of the particle. So we take two elements. We would say, well, iron has a molar mass of 55.85. Gold has a molar mass of 196.97. So that indicates it takes less mass to reach a mole of iron atoms. If I weigh 55.85 on a scale, I will reach a mole of these particles. But I need to reach 196.97 to get a mole of these particles. So it's a direct connection to the size of the particles by mass. Iron is smaller in terms of mass than gold, and therefore has a smaller molar mass. Whew. But that's the key hurdle to jump to, this idea, what does a molar mass really mean? And I keep repeating it because it's very important. We will literally use it till the end of the course. And then those of you going to 1A, you will be using it a lot there. And when you go to 1B, you will use it there. Now, actually, maybe this should be the point where we kind of take a breather. It's about the halfway point almost. So how about we do that? How about we take a break and then return? And that will give you an opportunity, if you'd like to ask questions, you can do so during the break in the chat. But let's go ahead and pause the recording. Okay, so as we're coming back, question. Going back to these elements, which weighs more, 1 gram of iron or 1 gram of gold? So let's see if I can trick you now. Which weighs more, a gram of iron or a gram of gold? And it's a trick, right? But yeah, they weigh the same. Okay, gotcha. But which contains more atoms, a gram of iron or a gram of gold? And that one. Okay, we got it. Yeah. So it's the iron. Remember, it's the same thing as the feather and the brick analogy. So which weighs more, a pound of feathers or a pound of bricks? Well, they both weigh a pound. But we trick ourselves because the feathers are lighter. So in the same way, the iron is like our feathers, where the gold is like our bricks. We might trick ourselves because the numbers make it seem like, oh, I should have some sort of difference between them in terms of their masses. If their masses are the same, what our brains are tricking us is the fact that the value for the molar mass of iron is small. So we might think there's less of it. But it's the same trick as the feathers versus the bricks. Don't let your brain trick you. If the molar mass of a substance is lighter, it means that there are actually more particles in equal masses. And so that means I want to be careful because this only works when it's equal. 1 gram versus 1 gram, 10 grams versus 10 grams, a pound versus a pound. When they're equal masses, the one with the lighter molar mass will have more particles in it. It's the same idea of you need more feathers to reach a pound. I need more iron to reach a gram because it's lighter. So, okay, I couldn't trick you guys, which is a good thing. I'm not trying to trick you. I want to make sure you don't get tricked by this, but very important that we get that idea of molar mass. Also important is to be able to calculate molar mass in different ways. So we have one more example. So for this set of practice on this slide, you will need your periodic table because, and this is an example of how we're kind of pulling off the training wheels a little bit. Questions from this point on might not tell you the numbers you need to calculate something, but you'll always be given the resources to be able to calculate, say, molar masses. So for example, if I say calculate the molar mass, so again, the practice is find molar mass in grams per mole, calculate the molar mass of fluorine gas, and I emphasize that there is a trick to this one. We should be able to know where to go to get that number, or get that answer, I should say. So what is the molar mass of fluorine gas? So why is this a trick? Because I'm not saying the element fluorine or the atomic fluorine. I'm saying you could extend this or connect this to maybe a real word. Maybe it's a balloon of fluorine or something. It's naturally occurring fluorine, right? It's the fluorine gas in that we experience. Of course, we don't actually experience fluorine gas because it's dangerous. It's not present on Earth in any sizable quantity. But if it were, it would be a diatomic 7. So this is a key difference. We want to also be mindful if we're talking about the element in its atomic form, or if I'm talking about a balloon of fluorine. Well, naturally occurring fluorine is, and that's why I emphasize to remember, is diatomic 7. So there is a difference between calculate the molar mass of the element fluorine versus calculate the molar mass of fluorine gas, because naturally occurring in our environment is going to be diatomic 7. And that matters because if I have a container of particles, right? If these particles are actually 2 glued together, we've now doubled their mass. So if we're trying to accurately calculate, we need to take into account that each particle is actually heavier than a single atom. And so it's going to be molar mass is 2 times what we see on the periodic table, which is 19.00. That's going to be 38.00 grams of, so this of F2, and I've run out of room, so I'll just do per mole of F2. And again, the reason being is that if we had a container, the particle would be an F2 particle. But to take a moment to just understand the idea, if I want the molar mass of something, I'm going to have to add up the atoms that are in each particle. So there were 2 Fs. I look up F on my periodic table. It's a halogen. So we should be getting more comfortable with that term. It's a halogen. So we see it, it's element number 9. And we say, okay, 2 fluorine atoms per molecule means 2 times the mass of 19 equals 38 grams per mole. How about calculate the molar mass? Again, these are all the same question. In 3.50 grams of sample of a substance that contains 5.60 times 10 to the minus 3 moles of molecules. So presumably, I mean, we can kind of visualize this maybe a little bit, is that we have a box, and somehow, some way, in this problem, we were able to count that there is a certain quantity of moles of molecules there. So we have this quantity of moles. And then we weighed those particles, and they weigh 3.50 grams. So what is the molar mass? of this substance. Remember, molar mass is intensive ratio. So the molar mass is grams per mole. Little m for mass, n per mole, 3.50 grams per 5.60 times 10 to the minus 3 moles of molecules, which means my m is 625 per mole. What I'm showing are different ways to ask for the same thing. All of these are find the grams per mole. This time we have a compound with the formula HC2H3O2. This is actually the formula for acetic acid, which is the main acid in vinegar, in case you were wondering. But what would be the molar mass of HC2H3O2? Again, alternatively, a molar mass is the sum of the masses of all the atoms. Only this time there are more of them, and they are different elements. We have carbon, we have hydrogen, we have oxygen. But the molar mass is going to be a total of 4 hydrogen, 2 carbon, 2 oxygen. So we look up these numbers on the periodic table. What's the number for hydrogen? Its molar mass is 1.008. Carbon is 12.01. And oxygen is 16.00. So that's going to come out to 60.05 grams per mole. All right, so that's another way we could ask for the grams per mole. We give a formula and say, what is the molar mass? It's adding up the masses of all the atoms and making sure it's in grams per mole. And then finally, what are the grams per mole for a DNA molecule that weighs 4.33 times 10 to the minus 20 grams? Whoops. So again, it's like we have a box, and inside this box, we have a single particle, a single DNA molecule, and it's very, very light, right? But what would be the molar mass? Well, this is one molecule. We want to scale it up to a mole of DNA. So just to do it as a conversion factor, so it's a little bit more transparent, I should say, is one DNA molecule is 4.33 times 10 to the minus 20 grams. So it is, as a conversion, we can actually write it as 4.33 times 10 to the minus 20 grams per 1 DNA, right? Because it's a relationship. 1 DNA equals this mass. But now I want my fraction to be grams on top, moles on the bottom. So maybe this way it's a little clearer why we're doing what we do with Avogadro's number. Well, 6.022 times 10 to the 23 DNA molecules are going to be a mole of DNA. So this is where that cancels. Single particle cancels, and we're left with our answer, which comes out to 2.61 times 10 to the 4. grams per mole. So 4 distinct ways to calculate grams per mole, utilizing the chemical formula and adding up atoms in the formula. One utilizing, it's kind of like density, where you put grams on top and moles on the bottom. And then one where we can take a single particle's weight and scale it up to how much does a mole weigh. So this is kind of our arsenal of what to do with those scenarios. But there's one other way we can ask what is the molar mass of a substance, and this one utilizes the gas law. So this is kind of a cumulative problem because it invokes our previous chapter, which is nice because it's always good to review in that way. So a 1.49 liter balloon of gas at STP, remember what that means, has a mass of 2.13 grams. What is the molar mass of the gas in grams per mole? So again, we need to utilize our givens. So we have 1.49 liters, STP, and 2.13 grams. So we are given a V is 1.49 liters. We're given STP, which we should know what that means. So standard temperature and pressure. So standard temperature is 273.15 Kelvin. Standard pressure is 1.00 atmosphere. And this is where it gets a little unique. We have a mass is 2.13 grams. What we desire is the molar mass in grams per mole. So what do you think we're going to strategize to solve this problem? What are we going to do here? So notice I have grams here, and my desired is also grams. So we can't count the atoms and add up using the periodic table because we don't have a formula. Okay, we don't have the mass of a single particle, so we can't use the Avogadro multiplied by Avogadro's number. But what we do have is a mass, and this is where we're going to utilize our sort of last definition of molar mass. Molar mass is intensive. It is grams on top, moles on the bottom, equals that, which we have. We have the mass. The only thing we don't have are the moles. That's what this is for. So we can calculate the moles because this is a gas. We can use the gas law. In this case, what is that gas law called? It's the ideal gas law. So that's exactly what we're going to set up. PV equals nRT, and we desire N. So we're going to divide both sides by RT. And we get N is equal to PV over RT. And then, as we did on the quiz, it's a matter of plugging in numbers. I think we're getting pretty good at plugging in numbers into the formula. 1.00 atmosphere 1.49 liters over 0.08206 atmosphere liter per Kelvin mole. And T was 273.15. Oh, oops, sorry. So we're going to plug that into our calculator. 0.06647. And our significant figures end here. But we're not done with the problem. So I'm not rounding. So by the way, I want to just clarify a little bit about the whole not rounding thing. Typically, when we're saying we're not done with the problem, so don't round. I just want to like walk back a little bit on what I said, which is I know I said don't round at all, but I'm noticing on quizzes like some people are putting like 10 decimal places. So thank you for taking seriously the not rounding rule, but you don't need to go that far. It's probably so generally going one extra digit over is good, but I always go at least 2. So just to let you know, you don't have to go 10 decimal places beyond. I thank you for the hard work. You can stop at like 2 more decimal places beyond what you need. That way it's not, yeah, I know. So just to clarify, I love it that you're taking seriously the not rounding thing, but you don't need to write that many digits. 10 is probably too many. Okay. So notice I went 2 more. And then that means the molar mass is mass over moles is 2.13 grams per 0.066474. Marking my sig figs. And so that comes out to 16 point. Oh, no, I'm sorry, it doesn't. It comes out to 32. Oops, okay. 32.0 grams per mole. So this is another way to get a molar mass, but for a gas. If we remember the definition of molar mass, it is the amount of mass necessary to have a mole of particles, but it also is an intensive property. It's the ratio of mass to moles. So in this problem, we were given the mass of the gas, and we wanted to calculate the molar mass. We need the moles. So that's where we use the mass that was given, and then we use the ideal gas law to get the moles to get this ratio, which becomes our final answer. So there we have it. This gas has a molar mass of 32.0 grams per mole. And now kind of bonus question, if this is a diatomic element, then what is its identity? So it's one of the diatomic 7. So that means 2 particles, whoops, 32.0. So a single one is 16.0, right? Which atom has a molar mass of 16? That's going to be oxygen, actually. Yeah. So we want to look for the bottom number. Remember, the bottom number is the molar mass / atomic mass. So we want to look for which element has a bottom number of 16, and that's going to be oxygen. So there we have it. One sort of last calculation for how do we get a molar mass. So again, molar masses can be calculated a number of ways, and this slide demonstrates sort of the 4 different ways We can ask the question, find the molar mass, but each of these is not interchangeable, meaning you can't pick and choose. Each one of these boxes represents how to do it given a certain kind of information you were given. So I want to just be clear, we're asking the same question, but your strategy has to be different depending on what the question gives you. So these are 4 ways that the question could be given, and with 4, some of them are similar, but also they're different in ways, strategies. As well as this problem in which we have to utilize the gas law to figure out grams per moles. All right, so now to sort of circle back and sort of connect it to the beginning, we're going to talk about the jelly beans again, except now we're going to sort of take off that analogy and replace it with what we really want to do, which is ask questions about counting particles in samples. So to turn the jelly bean idea into a chemical or chemistry question, we could ask how many CO2 molecules are in 305.8 grams of CO2. So again, it's like I have that container jelly beans, except I have a big box and it contains a quantity of, in this case, CO2, and I've weighed it. It weighs 305.8 grams. How many molecules are present in this? Maybe it's a balloon. So replacing our analogy, we're now counting the molecules in a container. And we have, instead of the mass of the jelly beans, we have the mass of the sample, the mass of the substance is this value. So now we ask, what do we do? Well, we want the molar mass to connect how heavy to how many. And in fact, that's a little jingle that I like to use. So question needs us to connect how heavy to how many. Notice that our quantity is in a number of particles, but our given is in a mass of particles. So whenever we have a question like this, it's a question that involves how heavy to how many. This is going to be a molar mass problem, which is our conversion factor. Now, we aren't given the molar mass. This is as far as the statement should go, and you should still be able to do the problem. So I say, not given the molar mass, no problem. How are we going to calculate the molar mass? Or find the molar mass, I should say. Molar mass is, well, it's grams per mole, but we can't use that strategy because we need to have that information. How heavy is the grams of the substance? How many moles are in the substance? We don't have that number, so we can't use that strategy. So we're actually going to use the other one, which is actually, to be honest, the simpler strategy. We count and add up all of the atoms. So the molar mass is going to be the 1 carbon and the 2 oxygen, 12.01 plus 2 times 16.00 to give us 44.01 grams per mole. So that's kind of the first thing. For these kind of problems, when we see that we're connecting how many to how heavy, this is going to be a molar mass problem, which is the conversion factor. And if we aren't given the molar mass, it should be a quick first step And again, with practice, it does become a quick first step to actually calculate what the molar mass is. It's just adding up the numbers on the periodic table. And remember, it's the bottom number. So how exactly is this going to work? Well, we can still do our givens desired. And we have 305.8 grams of CO2. And we desire molecules of CO2. So how is this going to work? Well, how heavy to how many means I'm going to use a molar mass. What does that molar mass convert our value to? Well, this converts us, this is a conversion factor that connects the unit of grams to moles. So it implies that we're going to have to do two steps. We can use the molar mass to convert to moles CO2. Now, danger, danger alert, a mole is not the same as a molecule. Remember, a molecule is an individual particle. A mole, so I'll say molecule. A mole is an entire group of particles. So just to be clear, so be careful with the spelling and make sure you're talking about what you think you're talking about, because I've seen that go wrong on quizzes. So one molecule versus a mole, a group of particles. So we are going to use the molar mass to get to moles. Okay, so that's using a conversion, that one we just learned. But now I have to connect the arrow here. So what goes here? That's going to be Avogadro's number. A group of things to individual things, Avogadro. But don't take my word for it. Let's just play around with these numbers. So we start with our given that we want to convert, 305.8 grams of CO2. I'm connecting how heavy to how many. So that means I'm going to go with, well, this is the relationship. It takes 44.01 grams to make a mole of this substance, CO2. So that's going to be, now we have to be careful to put the number in the right place. Remember, the number always goes with the unit right next to it. So the 44 has to go with the grams. So that means my grams of CO2 go on the bottom. My mole of CO2 goes on the top. And it's going to be 44.01 grams makes 1 mole. And that's going to be my conversion. So I'm going to cancel, cancel. It's never a bad idea to put the unit with what you're talking about. So grams of CO2. So notice that I'm doing that. I think it's a good habit. And in some cases, it helps sort of keep you sort of focused on what the task at hand is. So I encourage it. Now we're going to need to convert moles of CO2, or maybe, oh, I should keep it the same. Moles of CO2. Oh, I'm going to run out of room, so I'm going to extend my, there we go. And it's going to be molecules of CO2. There we go. So again, if it's confusing what to put where, remember, go back to the dozen analogy. A dozen is 12 things. A mole, 1 mole, so the 1 goes down. 1 mole is 6.022 times 10 to the 23 things. There's going to be our second conversion. That means I just need to plug this into my calculator. 305.8 times 6.022 times 10 to the 23, enter. Divide by 44.01. What we should get is 4.18 times 10 to the 24 CO2 molecules. So there are a lot of jelly beans in this jar. That's what we take away from this problem. There are quite a few jelly beans floating around. But this is how we calculate the answer. By knowing which substance we have, it's CO2 in this case, a maybe balloon of CO2, and knowing how much the CO2 weighs, so I put it on a scale, it's this much, I can use molar mass to go from how heavy to how many, and then Avogadro's number goes from a group to counting the individual particles. So that's the big connection we're going to have here. Did I make a mistake somewhere? 3.04. What did I say? 3.04. Oh, I did put 4 sig figs. Oh yeah. Oh, thank you for that. Yeah, it's supposed to be 4 sig figs. I actually don't know what that comes out to. Whoops. 305.8. Unless someone can tell me. By 44.0. Oh, perfect. Thank you. Oh, how funny. I didn't even notice that I did that. Does anybody recognize this number? The answer is 4.184 times 10 to the 24. Probably it's okay that you don't remember it exactly, but it should be a familiar. It's familiar to me because I use it a lot. 4.184. It is the heat capacity of water in joules per gram degree Celsius. I pulled these numbers out of thin air. So it just is a weird coincidence that this comes out to the same number, the same digits as the heat capacity of water. It's kind of funny to see those like just weird coincidences that come up. Anyway, I think it's funny. I should buy a lotto ticket. Yeah, the prize is pretty big right now. Apparently nobody won, so nobody won the big prize. Okay, a second sort of example. How many oxygen atoms are in 3.00 grams of Ca3ASO4-2? So this time it's a little bit different, but again, whenever the question is something that has to do with how many, meaning counting, and how heavy, that's a clue that this is a molar mass problem, because molar mass is the conversion between how heavy to how many. So this is that idea that we need a molar mass. Uh-oh, but this question ends, in one statement. We don't have a molar mass. Not given the molar mass, what do? We go to our periodic table and we count it for ourselves. So that's going to be 3 calcium, 2 arsenic, and 8 oxygen. Remember, it's because we have to distribute the number outside the parentheses. So we have to do that. When we do that, we get that the molar mass is 398.08. Oh, actually, AMU. Remember that this number does double duty. So it's both how much a single particle weighs in AMU, but it's also how much a mole of these particles weighs in grams. So that's what we have here. Now, our pattern or our task is to connect these dots. And I should emphasize that this question involves a little bit of the pre-lecture of how do we interpret the formula to become a conversion factor for us. So let's start putting these numbers together. We start with 3.00 grams of Ca3ASO42. Now, what can I immediately do? Well, I can turn how heavy into how many. It's 398.08 grams. Now this substance is kind of long to write, so I'm just going to omit it. But again, I'm referring to this. Actually, what I'll do instead is I'm going to just, and you can do this as well, just abbreviate it compound, because that's what it is, right? Compound there. That way you're still keeping track, but it's maybe less hassle to write. Is 1 mole of compound. All right. And this is going to mean we're going to cancel grams of this compound to moles. Now the question is, this isn't what we want. This is moles of compound, but we want how many oxygen atoms, which is a part of this substance. So what do I do as a conversion to go, I don't want the total compound. I only want to know how many oxygens are there. And then just to reiterate, the 398.08, that's by adding up the molar masses of all the atoms. So I did 3 calcium, 2 arsenic, 8 oxygen. It comes out to 398.08. So this is where we're at the point where now we want to go from the compound itself to just a part of the compound. Well, what is the relationship, the number relationship between the oxygen atoms and the compound as a whole? One compound equals 8 O atoms. And if you remember the pre-lecture, we can always scale up this relationship. So we could say 1 mole of compound is going to be 8 moles of oxygen. Either one of these is a correct relationship, and it shows that this type of problem actually has 2 different ways to solve it. So I'm going to use the 1 mole of this substance will have 8 moles of oxygen. One mole of compound has 8 moles of oxygen. And those will cancel. And now the last step would be, well, I have my moles of oxygen, but I just want to count individual oxygen atoms inside this substance. So I need to go from, and I've run out of room a little bit, a mole of oxygen to, and I'll just have to say O atoms. to go from moles to atoms, a group of things to counting individual things, that's Avogadro's number. So that's 1, and I've run out of room, so 6.022 times 10 to the 23. And there we go. We cancel them out. And we plug into our formula. So what does this come out to? Oh, actually, I don't have it. 3. And then we multiply everything in the numerator. And we divide by everything in the denominator. And we should get 3.63 times 10 to the 23. Oh, atoms. So again, the idea is like we're counting an ingredient in this box. So we have a bunch of particles. These particles are a compound, but what we're asking about is that if we sort of zoom in on these particles, so, not to scale, I don't want to spend a lot of time on that. But what we're doing is we're counting individual pieces of this substance. So it's kind of like you're counting an ingredient in the jelly beans. You're counting how much sugar is in the jelly beans. In this case, we're counting how many oxygens are in this compound. And to do that, we're going from how heavy to how many. That's going to be a molar mass conversion, except this time we also need to say, well, if I'm talking about an ingredient, a part of this substance, then I'm going to need to use the recipe or the formula to get where I need to go. All right. Alternatively, we could have done this using a different strategy. So if you thought of a different way to do this problem, there actually is another way to do this problem. So I'll pause and then say, what is it? Okay, I'll go ahead and answer. So it's after the first parentheses. So what we did is we chose to use the second definition of the formula, 1 mole equals 8 moles of oxygen. We could have actually used the first one, but it requires a sort of changing the order in which we multiplied the numbers. So if we did it using the second one, we would need to cancel out one compound. So that would require, instead of the second parentheses being what I have here, the second parentheses would be converting 1 mole of compound to individual compounds, and then using 1 compound is 8 atoms of oxygen. What that will do is basically it just reverses the order that you're multiplying these numbers, as well as we have to do minor modifications to the units to make sure they cancel again. But the math itself will come out the same. So there is a second way to do this problem that involves just reversing the order of the steps you do. Well, not reversing, but switching the order. Phew, okay. Oh, whoops, there we go. Grams per mole. Now, a final type of question that involves molar mass would be, what is the mass of calcium in grams that is in 855 grams of this substance, Ca3ASO4-2. Now, this one is a little bit different because it's not so obvious that this is a how heavy to how many, but take a moment to sort of read the question to yourself. And think about how the how heavy to how many actually comes into play. So in order to figure out how heavy a single ingredient is in this, how much calcium in grams is in the jelly beans, or our chemical jelly beans, in order to figure out how much calcium is there, I need to know how many calciums are there. So in this case, it's kind of a secret how heavy to how many, but it is one of those questions. It implies we are going to need a molar mass one more time. Oh, and this isn't part 2, this is part 3. Okay. So that means that we're going to have to do a couple conversions that we haven't done previously. We have the grams of compound, and we know now how to turn it into moles of compound. But what is it that we want? We want how heavy calcium is inside this. So again, it's like the previous question where we're only concerned with a part. So if we remember, we want to turn this into moles of the part. And from that, get to the grams of the part. So this is where the how heavy and how many comes into play. It's actually coming into play twice. So what we can first do is figure out, well, how many particles are in this substance. So that can be our first step. 855 grams of compound are present. Now this is the same substance as last time. So use molar mass from last slide. So to go back, that's 398.08 grams per mole. 398.08 grams per mole. And again, I want to say compound. So this will tell us how many moles of compound are present in my jelly bean box, whatever. So that's going to be our first step. But we don't want to know about the compound. We want to know about a part of the compound. So that's where we can use, again, the chemical formula will now turn our unit from compound to the quantity of calcium in this case. So what is that? One compound is 3 calciums. So that's going to be 1 mole of compound is going to be 3 moles of calcium. There we have it. And again, this comes from the fact that formulas are recipes. Remember in the previous lecture, we called it the law of definite proportions. It means that a substance will always have the same ratio of atoms in its particles, in its molecules. So water is always H2O. This substance is going to always be 3 calciums in each compound particle. And now we want to know how heavy is the calcium that's inside. In this case, we're going from how many to how heavy one more time. So I need to go from moles of calcium to grams of calcium. Where do I go to find the numbers to put into this fraction? That's going to be the periodic table, right? How heavy is a mole of calcium? 1 mole of calcium, according to the bottom number, is 40.08 grams. Cancel and cancel. We have now converted grams of compound to grams of just calcium. When we plug this into our calculator, we get, so equals 258 grams of calcium. If we were connecting this to the jelly bean idea, what this question is in terms of jelly beans is, say we were asking how many grams of sugar are inside this jar of jelly beans. Well, first I'd have to figure out how heavy are my jelly beans, then connect it to how many jelly beans there are, connect that to how much sugar would be in there, and then simplify to get the amount of sugar. So this question where what is the mass of calcium in this much compound is the same as saying how many grams of sugar are in this entire jar of jelly beans. It's kind of like an ingredient of that. Whew. All right. So we did a lot in this lecture, I will admit. So we have a tool set at our disposal that is specific for the question of how heavy to how many, counting particles by weighing particles. So first is our molar mass. It is a ratio. It is grams per mole. And it's used as a conversion factor between how heavy, grams, how many moles. But we should also remember that these questions could involve counting individual particles. That's where we'll also need Avogadro's number, where we can go from that unit, particles to moles, and back and forth. And then finally, what we learned in the pre-lecture and what we demonstrated in the last two problems is that chemical formulas are helpful to convert the big substance, the whole, to the part, right? An entire molecule has this many atoms in it. And so when I see H2O, I can turn it into, there are two H's in every water. There is one O in every water. We can do that both molecules and to atoms, or moles of the substance to moles of the atoms within it. And that was covered more so in the pre-lecture. But of course, if you'd like to talk about it, we can always do that. Feel free to reach out. But before we end, this is actually the end of our time together in lecture. I would like to direct you to Module 5, CP 5.2. There is molar mass practice. So again, in addition to the reviews that are naturally at the ends of subjects in modules, there is in this page a document with answers that goes through problems that we've seen today. So counting how many particles and so forth by weighing them. So that is what I will leave you with as we end this lecture. But that's it for today. The rest of this slideshow will be covered tomorrow or in our next recording. All right.